Hi everyone, welcome to Data Structures and Algorithms session 4.2. Session 4.1 we had covered the hash tables and especially chained hash table. This one will cover the uh, open hash table, and the presentation is going to be by Jamit Osawa, our study circle leader. He has been leading the various previous presentation starting from the fundamental, the series of C sessions, and now this is the DSA or data structure and algorithm session 4.2, which is part of the hash table. And with that, I will hand over to our expert, Jaimit Wasawa. Jaimit, go ahead and present. Thank you.
So thank you for the introduction. So hello everyone and welcome to the today's presentation of data structures and algorithm session 4.2, which is the continuation of the hash table, as also Prakash mentioned. So before starting the presentation or going to the core topics, first let's discuss a topic about which on the further uh, discussions are going to happen. Which is phases of the compiler design. So this is done because a related program is to be discussed and with respect to this topic. So what are the phases of the compiler? So what does a compiler basically do? It takes a source language and translates it into, while going through different phases. As the phases you can see the list one being listed, and translates it into the machine level executable code. So the first phase is the lexical analyzer, which takes in the source code and transforms it into lexemes. Lexemes are nothing but a series of characters, and stores them into symbol table and what they mean. And those lexemes are transformed into tokens, which acts as an input to the syntax analyzer, which is the second phase of the compiler design. So what we are going to discuss is about the lexical analyzer storing storing the lexemes into the symbol table, and symbol table through various phases is referred to again with all by whenever it is needed. So it is not a one-time thing for the lexical analyzer, but rather throughout the phase. What the lexical analyzer simply starts translating or scanning the source code and stores the lexemes into the symbol table. So what we are going to do is implement a chain hash table for the symbol tables. So an important application of hash tables is the way of compilers maintain information about symbols encoded in a program. So formally, a compiler translates a program written in one language, a source language such as C, into another language, which is a set of instructions for the machine on which the program will run. In order to maintain the information about the programs in a information about the symbols in a program, the compiler makes use of a symbol table. Symbol tables are often implemented as hash tables because a compiler has to store and retrieve information as quickly. Lexical analyzer groups characters into the source code into meaningful strings called lexemes. These are translated into syntactic elements called tokens, and that are passed on to the parser. Parser is nothing but the syntax analyzer, which is the second phase. The assumption that we are making about the program that we are going to discuss are this is a very simple lexical analyzer which takes two types of input. Either it is a digit or it is a non-digit, and we assume that the token are separated in the input stream by a single blank. The lexical analyzer is implemented as a function lex, which a parser calls lex is a function, so which a parser calls each time it requires another token. So components and the working of the program, the function works by calling the next token function to get the next blank delimited string from the input stream is stream. So stream is just an input stream from the source code, and next token is a token that will be generated. If the next token is equals to null, there are no more tokens to be generated. And the function uses a lexit to tell the parser that there are no more tokens to be processed. If the next token finds a string, some simple analysis is performed to determine what type of token the string represents. Next, the function inserts the lexeme token type together as a symbol structure into the symbol table and sim table and symbol table sim table, and returns the token type to the parser. The symbol is defined in symbol.h, which is a header file that we will be discussing further. So a chain hash table is a good way to implement a symbol table because it is efficient to store and retrieve information, and we can virtually have unlimited amount of data. So some of the interfaces of the chain hash table that were also discussed previously are will be used. So this is a chain table init for initialization of the chain table destroy, which is a custom destroy function for destroying the chain table or the deallocation of the chain table. Then or deallocation of each and every members of the chain table and destroying the chain table. Then chain table insert and remove for inserting and removing with both of their time complexity of big O of m, where m is the number of buckets in the hash table, and lookup chain table lookup and size for a constant time complexity. So this is a function for the chain table dot c. You can see different interfaces being applied over here from chain table init to chain table destroy, and then uh, further chain table insert for inserting the element, and chain table remove, and chain table lookup for looking up an element and that we want to look up to search for. So now let's so this chain table was also previously covered in the chain table hash tables chain table presentation. So now we'll be discussing about the program that we have to discuss for about the lexical analyzer. So these are the header files that we'll need. The ch table or the chain hash table, and that we just saw on the presentation slide. Then we define the token and what we need regarding it, and the and also the lex. Next, these are the required header files that we'll need. Then we define the token lex. Then allocate its the place or the memory. Then pass through it if there are uh, no more input or no more lex to be found or the tokens to be found. We use the lexit for exiting the loop. If we found it, we determine that type of the token, insert the symbol into the symbol table. Just a second. If the symbol that we want to insert is already available, we deallocate it using free function. And if it is not, then we return the token into the symbol table. So next is the uh, open addressed hash table. So in a chain hash table, elements reside in buckets extending from each position. In an open address hash table, on the other hand, all elements reside in the table itself. So this may be important for some applications that rely on the table being a fixed size. So without a way to extend the number of elements at each position, it solves the collision problem differently. So the way to resolve collisions in an open address hash table is to probe the table. So in layman's term, the probing is in context of hash table is like searching for an open spot in a crowded parking lot. When you arrive and find your preferred parking spot taken, you start searching nearby spots until you find an empty one. So similar to this one, in hash tables, probing is the process of searching for an empty slot when a collision occurs. Instead of immediately storing the item in the slot indicated by the hash function, probing involves checking another nearby slots until an empty one is found. This allows the hash table to accommodate multiple items that hash to the same index. So, assuming we are uniformly hashing, you have uniformly hash the number of positions we can expect to probe in an open address hash table is one divided by 1 minus alpha. Alpha is the load factor, and alpha's value is n by m. Example of an open address hash table that is half full means that the load factor is 0.5. The positions that we have to probe for finding the element is 2. So you can see that in the table now that if we have less than 50% of the load factor, which means the hash table is less than 50% full, and the expected probes are 2. But you can see that with the increase of the load factor, the expected probes are dramatically increased for the values. As we having less than 50 for less than 50%, the expected were 2, but for 95 we have 20. So the hash function for probing positions in an open address hash table, hash function for probing positions in an open address hash table is k of ki h of ki equals to x, where k is a key, I is the number of times the table has been probed thus far, and x is the resulting hash code. For an open address hash table, H must possess an additional property as I increases from 0 to m minus 1, where m is the number of positions in the hash table. All positions in the table must be visited before any position is visited twice. Otherwise, not all positions will be probed. So method for probing in open address hash table is linear probing and double hashing. We'll start with linear probing now. So linear probing is for h of ki equals to h dash of k plus I and mod m. So if we hash an element with for the given formula, if we hash an element with k equals to 2998 into the table of size m, the hash coding produced are for the value of I equals to 0 is 998. And similarly, for I equals to 0, we get the position 998. For I equals to 1, we get the position 999. And for the value of I equals to 2, we get the value of 0. So these are the positions that we will be looking after. If for I equals to 0 we didn't find, we will look at 999, and at 999 if we didn't find, we'll look at 0, and so on. So linear probing suffers from a phenomena known as primary clustering, in which the large chains of occupied positions begin to develop as the table becomes more and more full. So you can see in the image down below that for the first, we have inserted our elements starting from 37, 83, 97, and then for 78, 14. And after that, when we want to insert the element 59 uh, for I equals to 0 and 1, you can see how for different values to be inserted, the values are being searched for more and more unoccupied occupied spaces in order, and we have to find the occupied space, and more time is consumed. The another uh, type is double hashing. So after linear hashing, we'll be discussing the double hashing. So effective way of probing in open addressed hash table is a hash coding of two auxiliary hash functions. If we let I go between 0 and m minus 1, where m is the number of positions in the table, a hash function for double hashing is defined as h of ki equals to h1 of k plus I into h2 of k, where h1 and h2 are just different hashing functions, mod m. This ensures the elements are distributed in uniform and random manner. In order to ensure that all the positions in the table are visited before any position is visited twice, we must adhere to one of the following procedures. We must select m to be a power of 2 and make h2 always return an odd value. We must make m prime and design h2 so that it always returns a positive integer less than m. Now, this is continued further. So for the given formula that we just discussed, we let h1 of k equals to k mod m and h2 of k equals to 1 plus k mod m dash, where m dash is just a slightly lesser value than m. So if the hash table contains 1699 positions and we hash the key 15,385 or 15385, the position probed are by substituting the value for I equals to 0 uh, is 94, and for every 113th position after this is I increases. So for the advantage of the double hashing is one of the best forms of probing, producing a good distribution of elements throughout the hash table. And the disadvantage is M is constrained in order to ensure that all the positions in the table will be visited in a series of probes before any position is probed twice. So in the image, you can see uh, where first we have inserted the values from 37 to 14 with no collision. After that, we are inserting an element with k equals to 59 at I equals to 0, 1. 59 is inserted, then inserting an element with k equals to 25. It is probed, and now it is checking at 0th position and is saved. and inserting an element for 72, and it is saved or stored. So now we'll be discussing the open address hash table and its implementation. So let's just go through the interface of the open address hash table. So open address hash table or OSTBL init, I will be simply calling it init destroy insert for the open address hash table continuation now. So the init function will be initializing the open address hash table. So with with a return value of 0 if it's successful in initializing it, and -1 if it's not. And the destroy function for destroying the specified hash table, insert function for inserting an element into the open address hash table, 0 if the inserting the element is successful, 1 if the element is already present in the hash table, and -1 if it's a failure. Remove for removing the element, and matching the element and matching the data from the hash table specified by the STBL. Then a lookup for looking for matching for searching for the element and that we want to look up. Then size, which evaluates the number of elements that are present in the open addressed hash table. So this is the header file for the open address hash table that we'll also be discussing about in the future discussion. Here it is shown because some of the discussions will be done in slides before going into the program. So you can see the some of the you can see the implementation of the header files for the open address hash table. First we uh, first we construct a OSTBL member to the struct OSTBL. Then we initialize it. You can see the destroy, remove, lookup, and size function also, and how they are implemented. So now implementation and analysis of the open address hash table. So it fundamentally consists of a single array. The OSTBL is the open address hash table data structure. Positions in the OSTBL is the number of positions allocated in the hash table. Vacated is the pointer that will be initialized to special storage location to indicate that a particular position in the table has had an element removed from it. And it will use H1 H2 match. And vacated is also a placeholder or sentinel to remove for removed elements which will be probed. So uh, the basic reason to use vacated is because if we use a null value in the place of a removed element, and there are still uh, vacated or unoccupied spaces in the hash table, then null will signify the end of the hash table, and it will stop the function from probing itself further. So that is the only reason we'll be using vacated function separately in order to avoid that. So null actually means to stop and will use null only or null will be only used in the hash table when we actually mean to stop probing. Then a table is array uh, in which the elements are stored. So the bolded parts are actually the way they are used in the program, and just in case if someone didn't notice. Then we'll be discussing the functions that how they will be implemented apart from the one that were mentioned before, apart from the one they were earlier mentioned. The initialize function in an open address hash table is a simple operation in which we allocate space for the table, initialize the pointer in each position to null, encapsulates the h1 and h2 match and destroy functions, then initialize vacated to its sentinel address and set the size member to 0. Then the destroy operation destroys an open address hash table. Primarily, this means that freeing the memory in it or located for the table. Then the insert function, the operation inserts an element into the open address hash table. Since an open address hash table has a fixed size, it makes sure there is no room for insert. Key is not allowed, so we use a lookup for it to contain the element. If conditions are met to insert, we find an unoccupied position in the table. We set the pointer at that position to point to the data we wish to insert. After this, we increment the size of the table if because we have successfully inserted the element. Then for removal, the operation removes an element. The OS table removes an element from the hash table. To remove the element, we use double hashing uh, uh, as an insert to locate the position at which the element resides until null is formed. We find the element, we set the data to the data being removed and decrease the table size by 1. We set the position in the table to the vacated member of the hash table data structure. Remember that we will be using vacated for signifying the removed members or elements from the table. So for lookup, the operation searches for an element in the open address hash table and returns a pointer to it. Now let's refer to the code for the open address hash table. So this is how the header file will be created. We first define the structure, then have the element, and then this is how we are going to implement the init function for it. Then the destroy function, the insert function, the remove function, and the lookup, and in the end, the size of the table. So now let's look at the actual program of the implementation of the open address hash table. First are the included header files. Then we reserve a place for the vacated elements. Then we initialize the table. Allocate its space and initialize each position. Then we set the vacated member to the sentinel memory address reserved. Then encapsulates the function and initialize the number of elements in the table. Now, after initializing, we'll discuss the destroy function. So, this is how we'll be applying the destroy function. We'll traverse through each and every element, destroying, and then we'll be destroying the elements while checking whether there are more elements to be destroyed, whether there are elements present in the table or not. Then for inserting the element, first we will check whether the size of the table is not exceeding the number of positions in the table. We'll check whether the element is present in the table or not. Then we'll pass through the data and check for the unoccupied space and insert the data and increase the size. If for some reason and that we are not able to perform the insertion, then it will uh, just give us the passcode of -1 for the failed operation. For removal of the data, okay. First, we'll go through the elements to search the removal. Search for the element that is to be removed. If we don't find it, we run -1 for the failure to find it. Then we'll search for the elements further. As you can see, beyond the vacated positions. And if we find the data, we pass back the position to be removed, and you can see the operations over here, from the position to be done and on the vacated, and we decrease the size of the table. And for the successful operation, we return 0. If for some reason we are not able to still find the data that we want to remove, it will give us a failure returning -1. Then in the end, for lookup of the open address hash table, first we'll try to find the element within the table. If it is not, it will return -1. If it is, we'll pass back the data to the table while passing through the table, going through the table. If still for some reason we are not able to find the data, we'll return value -1 for its for the failed operation. So this was some of the implementation of the open address hash table, and with the use of interfaces and how it can be applied. So now, before ending this session, let's go through some of the questions and answers. In the implementation of the chained hash table presented, the actual hash code used for the accessing the table in the hash code modulo the table accessing the table is the hash code modulo the table size. Why is this? So this transformation ensures that the hash coding does not position us past the end of the table, and the hash function ensures that it is worthwhile for the hash table implementation to provide the guarantee as well, especially since the hash function is provided by the caller. However, it is not the same reason that the modulo is performed when double hashing. The process of double hashing may produce a hash coding that falls outside the bounds of the table, even for two auxiliary hash functions, each producing hash coding within the table. This is because the hash codings are added together. Next question is, why are hash tables good for random access but not sequential access? For example, in a database system in which records are to be accessed in a sequential fashion, what is the problem with hashing? So hash tables are good for random access, and hash tables are good for Hello?
Yeah, continue.
Yeah. So hash tables are good for random access, but it does not support sequential access. So we have no way to determine where the next smallest or largest key resides. So comparing this with the linked list, we always have the next element to point to. Next is what is the worst case performance of searching for an element in a chain hash table? How do we ensure that this case will not occur? So, one way it can be is because uh, in one single bucket, all the elements are hashed to, and that will make the searching of the element of all the elements that are present in the bucket. So a hash function of you can see that h of k equals to c, where c is some constant within the bounds of the hash table, and selecting a good and to avoid this, what we can do is selecting a good hash function which can uniformly hash the table, uniformly uses the hash function and uh, spreads the element across the table. So, question 4: what is the worst case performance for searching element in an element for searching for an element in an open address hash table, and how do we ensure that this case will not occur? So, the searching of an element is an uh, in an open address hash table occurs once the hash table is completely full and element are we are searching for is not in the table. So this case can occur with any hash function. So to ensure the reasonable performance, as also what we have discussed in the table that we have seen, that we should have the probe positions of 2, or the load factor of 2. You can see what I mean by the table that we have referred to before. The For the load factor having less than 50% of occupancy, you can see the expected probes to be 2. And as we keep on increasing, as the occupancy is more and more increasing, the expected probes are dramatically increasing. So, for a more detailed explanation, you can read the answer for question 4, what we are discussing right now. So, yeah, this is the whole presentation on the open address hash table. And next, we'll be covering a different topic on the data structures and algorithm. So, thank you for listening. Thanks a lot.
Jamie, thanks for the very good presentation today, and look forward to the next session, which will be on the trees. So I hope we will be able to do it on Friday, in another 2 days. At least tree session 1, we'll be able to cover some of the simple trees, and then we'll get to the Saturday session if needed to cover examples, etc. I hope you are ready for it, and
Yeah.
thanks for the question and answers, and all recording will be posted in another few hours. Hopefully, let the students and the listeners who review the slides and the records can come back to us. And thank you very much, and look forward to seeing you next session on Friday. Okay? Thank you. I'll stop the record.